Hello everyone, good afternoon. I managed to make it here. Air traffic control in the UK tried to stop everyone from flying, which was nice on Monday. I ended up having an extra night with my family in a hotel in Greece, which is not the end of the world. I've got the sunburn to prove it, actually. My name's James, thanks very much for coming. My name is James Lewis, actually. I work for a company called ThoughtWorks. So we're a software development consultancy. We've been going around, I guess, nearly 30 years now. I've been working with ThoughtWorks for the last 17 of my career. Before that, I was doing a bunch of other stuff. And these days, I genuinely haven't got a clue what I do for a job. I do a lot of this. I don't know what this is, marketing, DevRel, whatever that is. I'm not selling anything, though, so... And I spend quite a lot of time advising our clients, specifically sort of more exec level these days, on how to get better at building software, how to get better at actually organizing themselves into different team structures, different team topologies, and how to build software architectures that enable flow, so the flow of value, the more effective flow of value. This talk is a sort of a newish one. I've done it once or so before, twice I think, maybe 3 times. Neil Ford, my colleague, he always says that you don't actually know what a talk is about until you've done it 4 times. So hopefully after today I'll have some idea, we'll see. And hopefully you will too. It's really an exploration of what's been going on in my head over the last 5 or 6 years. In terms of my understanding of how teams generate value for their organizations, for our customers. And how different team structures, different ways of organizing, different types of sort of patterns like self-service versus ticketing and things, how they sort of interact to either make us more effective in an organization or less. And also my fascination with something called complex adaptive systems, or complexity science. So I've been fascinated by complexity science for about 15 years now, and I've been following closely the Santa Fe Institute and the work they've been doing. And amazingly, we're at the cusp, I think now, with Gen AI, of being able to use some of the ideas from generative science and complex adaptive systems to actually simulate organizations and organizational designs, and to actually ask questions in software of how best we should structure our teams, and via Conway's law, therefore structure our software architectures, and vice versa. So that's what this is about, how work works, and other curiosities. And there are some curious things in this talk, I think. But first, I'm going to go back to a bit of sort of history. So life moves pretty fast. If you don't stop and look around once in a while, you could miss it. Of course, the great Ferris Bueller. Now, I've been a member of the ThoughtWorks Technical Advisory Board for about 11, 12 years now. One of the things we do in ThoughtWorks is produce something called the ThoughtWorks Technology Radar. A quick show of hands, who's come across the Tech Radar? It's not that many people, fine, that's good. We produce this thing, it's like a snapshot of what our teams are doing globally every 6 months. So what tools, techniques, kind of platforms, languages and frameworks that our teams are currently using, the current state of the art for our teams globally. There's about 12,500 of us globally now, so that's there's a lot of developers writing a lot of code, a lot of testers testing a lot of code, and some of the insights we try and feed into this thing called the Tech Radar. And the interesting thing for me is, having published it for such a long time, we get to look back and take a look at some of the sort of insights, or take a look back in history as to where some of the things we take for granted now, I guess, come from. You might think that life is moving, technology is moving faster and faster. And in fact, our research, or our anecdotal evidence from the radar, backs that up. Every 6 months, we have about 300 new things to talk about. Every 6 months, 300 new things, never mind the things already on the radar, and there's about 100 of those. But even that 300 is a small amount. In India this year, before coming, my Indian colleagues, before coming to the radar meeting, they discounted over 400 items as not being interesting enough to bring to the meeting. So if you think there's thousands of new patterns, tools, techniques happening every 6 months, but it's useful to take a look back and see where some of these new things come from, because it's quite surprising sometimes. So if we go back to 2011, which is about when we started publishing the radar, we started talking about Android. Android was on our radar back in 2011. That's how new that is. That's 12 years ago, right? I mean, obviously it was invented before, it was created before that, but that's when we started talking about it. We started talking about distributed version control systems back about the same time. Of course, Git has now eaten the world, but we were talking about Mercurial at the time as well as being a super awesome distributed version control system. And then AWS. We started talking about AWS back in 2011. Of course, it was created a bit before that, but in 2011, ThoughtWorks became the first ever Amazon Web Service training provider. And I know this because I was training person number 4. I was the 4th person in the world to do Amazon Web Service training, and we put some courses together, and it was all awesome. And I'm thinking that Amazon wouldn't want to be in the business of training in the future or certification. Yeah, turns out that's not the case. They did quite want to get into certification and training a bit later on. But for about 2 years, we were the only Amazon training provider. And, back then, who'd have thought Amazon Web Services would have been a thing? This is about the slides from our training course. They only had very few services and features compared to now. There we are, ThoughtWorks, our old logo. Those were the partners at the time. But who'd have thought Amazon Web Services would have been a thing? But then that begs the question, why is Amazon Web Services, or you can exchange that for Google Cloud or Azure, why are self-service infrastructure platforms so popular? Why have they eaten the world? Why have they taken over, essentially, in terms of how we host software? Well, this is the answer. I will unpack this a bit later, but infrastructure as a service platforms are MMCQs where C tends to infinity. Now, obviously, everyone's au fait with queuing theory notation, and yeah? Nope. Anyone got any idea what any of that means? That's good, because I'll explain it a bit. But this is why AWS has eaten the world, and why self-service cloud is eating the world. Simply, they provide MMCQs where C tends to infinity, simply. Then, just after sort of 2011, about 2012 or so, continuous delivery, that sort of appeared on our radar. We've only been talking about continuous delivery for 10 years. And that's amazing. Before that, that wasn't really a thing. We weren't talking about continuous deployment of software through build pipelines into production. That's only been going around about 10 years. Just after that, we have microservices. Now, I'm, I guess, the grumpy uncle of microservices. If you haven't read my bio, I kind of was one of 3 people, I guess, in the world who can claim to have invented the idea of microservices. Myself, Adrian Cockcroft, who was there at Netflix at the time, and a guy called Fred George. And I wrote up microservices on Martin Fowler's site with Martin, and that's sort of the original definition. A quick point about microservices these days. This is from Twitter today, in fact. Someone bemoaning the fact that even like small, tiny teams have suddenly decided that they need like 15 microservices, 10 databases, and every time you go for an interview, you need to know the ins and outs of distributed system design. Now, I have some sympathy with this. Microservices were developed as the architectural style of microservices were a response to giant monolithic architectures that we had back previous to sort of 2011, we still have today. So I'm going to go on record in this room and say there is nothing wrong with starting with a modular monolith. My problem is that modular monoliths grow and grow and grow. They don't stay modular for that long. And, I'm too stupid to actually build monoliths in a modular way. So that's why we invented microservices, because I'm too stupid to build good, well-designed monoliths. But this is a real thing at the moment. Microservices are kind of, should we be using them, should we not? But they've only been around, really, as a pattern, as an architectural style. Service-oriented architecture predates it, obviously, since about 2014. Docker, slightly later, latter half of 2014, we started talking about Docker on the radar. Then we started talking about Kubernetes just after that, about 2015. Now, if you think about microservices and Kubernetes and Docker are kind of almost like synonymous these days. You don't do microservices without Kubernetes. Kubernetes has only been around a really short period of time. And then, starting on some other few things, we've got React started appearing in sort of 2016, I think this was, and that led to this kind of massive explosion in JavaScript, although it predates React, but React was part of this giant explosion in JavaScript. I know Prag Dave from the Pragmatic Book, Dave Thomas, he had a great tweet, which was, I don't know what MVC library I should be using for JavaScript, because I haven't checked Twitter this morning, which is, kind of modulo. It's the old ones are the best, they say. But interestingly, we started talking on ThoughtWorks about JavaScript as a first-class citizen way back in 2010. JavaScript as a first-class language. Then we started talking about treat all code the same, whether front-end or back-end. We weren't doing any testing of JavaScript 10 years ago. That's all actually applying proper engineering to web front-end. That's all happened in the last 10 years, amazingly to me. Then we have React, then we have something called platform engineering teams started appearing in 2017. So this is the idea of platform product engineering teams, building a platform on top of your infrastructure services, and offering self-service access to those platforms to your development teams. This has become incredibly popular, except no one ever does it properly or right, I think, or rather many organizations don't get the benefits of self-service platform engineering teams. This is from an article my colleague and friend Evan, former colleague, Evan, he's still my friend, he's not a former friend, Evan Botcher, he wrote for Martin Fowler's site. He called this the half-arsed private cloud pattern. So this is when a large organization, they basically put an API over their operations team, and they call that their private cloud. Except you've still got a bunch of people behind the scenes servicing tickets and so on, right? Actually, just to put in an API over your ops team is not going to solve any problems, or make you go faster. It's the second part of this comic. I just heard about this thing called the platform. Apparently it comes with the DevOps. Oh, sure, why not? Let's have one of those. Okay, boss, we've implemented a DevOps. We still have a platform too, but we still can't get anything done. And that's really a thing, right? Often organizations I talk to spend hundreds of millions of euros, actually, in some cases, certainly tens of millions, of trying to implement these self-service or trying to implement platforms and platform engineering teams and don't really get the benefit or don't get much return on that. So I did promise you I'd cover what MMC means in terms of queuing theory. I'm trying to explain to you why Amazon is a thing and why self-service platforms are a thing and why most platform engineering efforts fail or don't provide the value they should using some queuing theory notation. So what we start with is a queue, right? So this is a queue of stuff. You've got stuff coming into it in sort of jargon, I guess. You've got producers, which is and lambda is the rate of arrivals into a queue. You've then got a set of nodes that service requests going into that queue. Then you've got departures from the queue. That simply is that's kind of the notation we use when we talk about queuing theory. Now, I have this MM1 or MMC when I was talking about MMC. What this means essentially, it talks about the number of service nodes, we've got that little circle, servicing the tickets or the requests being put onto the queue by the producers. Right? That little thing at the end, the 1 or the C, that denotes how many people or how many things you've got servicing requests into your queue. So an MM1 queue, forget the MM bits, that's about the distribution of arrivals and departures and so on, and the rate of processing. But the MM1 bit, the 1 bit means you've got one thing servicing requests. So if you think about in your normal operations environment, right? You're in an ops team, you've got ServiceNow, and someone requests a virtual machine, and there's only one of you on your team that can create virtual machines. You're the one in that system, right? You're the one in the MM1 queue. And the rate at which you can provision and provide virtual machines or databases or anything else is as fast as you can provision them, right? That's pretty much as fast as you can go. The only way to scale operations is by adding people. So this is what the C means in MMC. C means a number of nodes, a number of servers, a number of processes that are able to provide a service or service tickets, if you like, for the queue, where C is the 1 to C, whatever. So if you're in an ops team, the only way to get faster and to provide better service if you've got a ticketing system, is to scale the number of people. You hire more expensive people to create VMs or to create databases or whatever it is. Right? And at some point, you're either going to run out of people to hire, because there aren't that many, or you're going to run out of money in which to pay them. Right? So you're always going to be hit a limit, essentially, of how fast you can service the requests for stuff from your delivery teams. There are actually 4 different types here, right? So on the first case, you've got a traditional ops team, where you've got a delivery team creating requests for stuff, or databases, or whatever it is, infrastructure, test environments, and so on. And that's denoted as an MMC queue, where essentially C is the number of people you can afford to hire to service those tickets, to service those requests. In the half-assed private cloud world, which my colleague Evan Botcher described, this is the same as having a traditional ops team. You just put an API over ServiceNow, right? You still have to scale people behind it to get stuff done. So actually, you don't get any faster by putting an API over your superficial private cloud, your ops team. Infrastructure as a service, or self-service, AWS, Google Cloud, etc., Azure, the other cloud providers that are out there, they have a different model, right? The self-service model essentially means they've got an infinite supply, more or less infinite supply, of services or servers that can process requests. Right? This is why Google and the cloud providers, this is why it's so attractive to delivery teams. Because suddenly, you just issue a request, you get a thing. But you don't have to wait to the limit of the computing power that they've got available, and so on. Right? But this is why you get to go so much faster as a team using infrastructure services like self-service clouds. You've then got the 4th option, which is the worst of all possible worlds, and this is the half-assed platform engineering team. This is the situation where you've got a platform team which you have to ask to build stuff for you, right, before you can use it. So, hey, can you just create me some new firewall rules or whatever? And they'll say, well, we're going to provide you a self-service way of doing that, but you have to wait a bit while we build the feature. So you're putting, again, requests into their queue, and you're having to wait for them to do stuff for you. So essentially, you get rid of all the benefits of the one above, which is infrastructure as a service. And this is why so many of these platform engineering efforts fail, because you don't actually get what you're paying for. You don't get to go that much faster. Unless you're providing self-service access to things in your organization, you don't get the scaling effect of infrastructure as a service. So just to summarize this, you've got these different types of things, these different types of queue. Most of them are expensive and slow and require you to hire people to scale the number of requests to your delivery teams. But this is why AWS is a thing, right? This is literally why AWS 1 or the Google, or the cloud providers are so impressive. And this is why we should think long and hard about limiting access to this sort of infrastructure in our organizations. Yes, there are reasons, security, compliance, and so on, but actually the self-service thing is the thing that makes us go fast. That's a bit of a sidebar for you. That's why I had to get the flash in, because why not? Sidebar, platform engineering teams, queuing theory. We'll come back to queuing theory in a bit. It's through a lot of this talk. So happy days, right, if you like queues. Then we've got data mesh. This is like microservices applied to the data landscape. And then back into more current times. And suddenly you've got this explosion in Gen AI, in data engineering, mainstreaming of ML, and so on. Wouldn't be a talk in 2023 without talking about LLMs, large language models. So this is an interesting article on Martin's website by one of my colleagues, our head of tech in China, about how he uses prompt engineering to make his team go super, super fast. Also, BT, apparently, we're all going to be out of a job. This is going to be awful, and the end of the world is nigh, etc., etc. Kent Beck saying, oh my God, most of what I do is useless, etc. And I was at a futurology event. There are these things, a futurist sort of event. And they were talking about the differences between, when you get these giant new advances in different industries, the effect actually on the economy and so on. And they were sort of talking about how, when the car was invented, suddenly you had this huge explosion in the number of cars. You had this explosion in related industries. You had a huge amount more jobs available in sort of tangential occupations and so on, and how Gen AI is going to do the same thing. It's going to provide lots of different stuff that we were going to be able to do. And the person on after this futurologist, who was very positive about the future, he put this line on the graph and said, yes, the problem is, if you look at this from the perspective of the horse at the turn of the century in the US, it didn't look so good. So even though the number of cars went up, the horses went down. So are we the horse or are we the car? That's the question, I guess, posed at this point. But I'll move on, because that's just the thing I have to do. It's contractually obligated to do that, talk about Gen AI at some point. So that's where we sort of come from. What I was hoping to sort of point out is a lot of the things we take for granted, things like continuous delivery, things like containerization, things like self-service access to infrastructure in the cloud, and even modern front-end frameworks like React are super, super new. Like, they're still evolving really, really rapidly. But I think we are triangulating around a set of things that, as an industry, we can sort of hang our hat on and say, we think these are sensible defaults, if you like, which I'll come to in a sec. These are things that we can use to sort of provide a set of engineering or some engineering rigor around the things that we do in our world of work as technologists, as software engineers, and related folk. So this is the set of ThoughtWorks sensible defaults. This is what we would consider to be the minimum set of practices that we would expect to see on all of our projects. Thought I'd put these up there because it often surprises people that we still are firmly sort of behind the sort of XP practices. So frequent continuous integration, test-driven development, pair programming, building security in, fast and verified automatic build, so continuous delivery, continuous integration, automated deployment pipelines, et cetera, et cetera, et cetera. Build for production. Now, these are the things that I would expect. In fact, when I do our inductions for new people coming in, I sort of say, if you don't see these things on your project, this is a massive red flag, and you should be raising it to the people who are providing sort of oversight, if you like, of your project or of your product. Because if you're not doing these things, I don't think we're doing engineering. I don't think we can call ourselves software engineers. These are the set of practices that we can use to ensure that we get repeatable results most of the time, right? I can honestly say that in ThoughtWorks, I can count the number of projects I hear about that fail probably in my last 17 years on two hands. So that's a pretty impressive, I think, track record, and it's based around engineering discipline. We talk about Agile, fine, we can talk about Agile all we like, and processes and flow, but actually engineering discipline is the thing that all this is based very much firmly upon. Which brings me to this section. So I think there's a set of sort of canonical books now out there, canonical works that we can point to that sort of encapsulate a lot of this work. So the first would be Continuous Delivery. My two former colleagues of mine, Jez and Dave. The next one would be Building Microservices by Sam Newman, and then Building Evolutionary Architectures. So these talk to how we get stuff repeatedly and reliably into production, talks to how we can repeatedly and reliably scale software, and these talk to how we can repeatedly and reliably sort of, evolve software using things like fitness functions and so on from evolutionary architecture. But then there's also the principles of product development flow. So this is about how we can think about our job as a process of getting information, turning information into value through a series of value-adding activities. Principles of product development flow. I'll come to that in a sec. There's Accelerate. Accelerate sort of describes a set of metrics that we can use to understand how healthy we are as a development team, and therefore across our organization, many development teams. The Accelerate metrics are like sort of taking your pulse or blood pressure, if you like, going to the GP. So things like, mean time to recovery, cycle time, availability, reliability, change failure rates, and number of deploys per unit time. This is like how healthy we are as a team. It won't tell you if there's anything wrong or if there's anything particularly right, but it'll tell you if you're, whether you need to see a proper doctor or not. So that's kind of like Accelerate. And then finally, there's, I think, a recent addition to the canon, which is Team Topologies. Now, who's come across Team Topologies? Yeah, quite a few hands coming up. Now, Team Topologies, I think, is one of the most important books that's been written about what we do in terms of how we organize ourselves to get stuff done, to get shit done, basically, right? So Team Topologies gives us a language that we can use between ourselves to say, well, what sort of team shapes should we be looking to implement in our organization, and therefore, what types of software architecture will come out. They talk about 4 different types of team. They talk about value stream aligned teams in this. So building teams around the flow of value through with the flow of value to a customer at the end. Amazon Web Services, or Jeff Bezos famously, he sort of said that all Amazon's teams should have a direct line of sight to the customer. That's what value stream aligned teams are all about, having a direct line of sight to an end user, to a customer. Then they talk about platform engineering teams. I think I've covered that, and I think I've covered the bad part of platform engineering. But self-service platform engineering teams making the rest of the organization go faster. They then talk about 2 different other types, one which is sort of consulting function, and one which is to do with very complicated software. So you might need complicated subsystem teams or sort of other specialist teams. But it gives us this ability to talk amongst ourselves about the way we structure our organizations reliably across different organizations. So I've sort of got this I've sort of structured this into 2 different parts. Stuff we do that seems to work, and then how it works, right? So the sort of mechanics, the structure of underneath how this sort of stuff works, how work works. Another quick sidebar. If you haven't come across this book, Dave Farley published this during lockdown, Modern Software Engineering. In this, he argues very strongly that actually, previously, it was pretty hard to call ourselves actual engineers. If you look at actual engineers, actual engineering, the set of processes that have been picked up over many, many decades and in some cases thousands of years for things like civil engineering and so on, the kind of the mathematical rigor that goes behind stuff. What we do seems often a lot like art, or a lot like craft instead. In fact, there's a funny story. Lots of space stuff happening in this event. And I was at an event with an amazing woman, Dr. Anita Singh Gupta, and she was the principal investigator for the Curiosity landing stage. So the Mars rover, the Curiosity, the landing bit, when it got to Mars, it had to land, and it did all this weird retro thrusters, and there was like a lander thing that flew off, and it's all crazy stuff. And at the end, she did this brilliant talk about it. And she asked for questions, and there was someone in the audience, a software developer, who said, right, well, what do you do about redundancy? What would you do if something failed? Did you build redundancy in? And she just doubled up laughing. Which I always thought was brilliant. She started laughing. And then she says, no, we can't build redundancy in. We can't put redundancy on board these things, because redundancy means weight. Right? And as soon as you add weight, you add in tens of millions to the cost, because any time you add weight, you've got to add more fuel, get out of the Earth's gravity well, and so on. No, she said, we use this other thing we like to call engineering. And there's 2,000 software developers in the room went, oh. But Dave in this argues quite strongly that, looking at the sensible defaults I just sort of mentioned, things like continuous delivery, things like shifting left on testing and security, automated build pipelines, automated paths to production, these sorts of things, we are approaching the point at which we can sort of say, yes, we've got a way of sort of, safely and sort of sustainably replicating our processes to produce optimum outcomes. And I know lots of people will disagree with things like test-driven development and so on. Personally, I think it's part of what we need to do to call ourselves professionals. There we go. Now, on to the next bit of this talk about how work works, which is about how work flows through teams. I mentioned it sort of briefly with the queuing theory piece, how work is flowing. We raise tickets, and ops are going to take a ticket and they're going to create a VM or whatever, and then we can use the VM or a database or whatever that is. But essentially, all work is like that. Like, if you think about what we do in our day-to-day life, we're taking stuff, right? Usually sort of a collection of whether a user story, or if you're a lawyer, maybe it's a brief, right? We're doing stuff to that thing, writing some code, maybe testing some code, and then something pops out the other end, whether that's a BA that creates the user story from maybe an epic or something else, or a broader feature, whether it's a software developer who's taking some code, a user story, and implementing some code, or a tester. The output is code, the output is tested code, and so on. Essentially, what we're doing is providing, we're taking bits of information and we're enriching that information to add value to it. That's essentially what we're doing in our day-to-day lives. Sorry, I know it's a bit depressing. That's literally, we could be replaced by machines, more or less. No, there's one person smiling, so that's good. My sense of humour isn't quite as dry as the Icelandic folk that I've met, but it's fairly dry. Has anyone been to Iceland? Is anyone from Iceland? No. I couldn't, honestly, Iceland was, if you get a chance, it's an amazing place, but I genuinely couldn't tell whether anyone I spoke to was telling me a joke or whether it was actual serious. It was just, honestly, I just couldn't understand whether it was, yeah, anyway, Iceland, brilliant place. So, value stream maps. Value stream maps, if you haven't come across value stream maps, they're a brilliant way of mapping how work works, right? How our teams operate, how value flows from the idea, an idea being created through into production or some production-like state. And value stream maps, they have a series of activities on them generally. So in this one, is that still working? Yeah. So in this one, we've got 3 activities. This is from a real client. It was a very simple process. They had essentially software, writing code at the front, then they had testing and deployment. On average, it took about 3 days to implement a user story. It took about a day and a half of testing afterwards. They were doing a sort of waterfall-y thing, and then about half a day to deploy. Which, looking at this, you can look at the value stream map, and it'll tell you the value-adding activity of your team. So in this case, it's 3, 1.5, 4.5, 5 days of value-adding activity. But a user story entering this process waits for 2 days for it to be picked up on average, then gets some work done on it, then waits for 10 days before testing happens, and then waits for another 30 days for the release train to come around and that code to be deployed. So what this value stream map shows you is out of the entire production lead time, which is 47 days, it takes 47 days for a piece of work to flow through this process, the value-adding time is only 5 days. That means you've got 42 days of work sitting around, inventory, essentially, sitting around rotting, to mix a metaphor with the retail world. So if you're a supermarket, you don't want inventory sitting around because it's going to go off, right? It's the same with what we do. You've got inventory sitting around for 42 days, not earning you money, right? If you got that into production 42 days earlier, how much money could you have made? And that's compounded by every single piece of work that's being done by this team. This is why value stream maps are really useful. They give you an idea of what you could have won, right? Of how much money you could have made if you optimized your process. And often optimizing your process is really, really simple. I'll come on to some of those tips in a second. But for example, if this team deployed twice as often, instead of 30 days, they deployed every 15 days or every 2 weeks or whatever it was, they would immediately slash this amount of time it took to get stuff into production, right? Massively improving their throughput and making lots more money just by deploying twice as fast. Now, obviously, value stream maps in most organizations, big organizations, don't look like that. They look more like this, right? So this is from another client of ours, who I won't name. Up here is where like a business case is being created and generated. So right at that end. Over here is where code is actually running in production and earning some money, right? So all that stages of process is to do with, creating requirements, generating software designs. There's a bunch of people in the middle that they just go around in a circle updating their own canonical data models. They've got 2 of them, 2 canonical data models. They didn't get the memo on what canonical means, I think. I think it means 1. So they've got 2 of these things. They just update each other's. You finish it, I'll do mine. And then there's a tiny bit, I'm not sure if the laser is going to work. That blue post-it there, for those of you on this side, that blue post-it there, that's code being written. We didn't bother putting all the amount of time it took to go through this process on, because by the time we'd actually drawn it all out on a wall, the IT director looked at it and just he basically had a tantrum. Why are we doing this? So we didn't even have to bother adding any more information to it. But these value stream maps, they're super, super useful because they show you different types of things you can do to get faster. And they show you different types of what we call sort of wait times, essentially. Different reasons why you might have to wait on other people to get stuff done yourself. This is all part of how work works. The first is coordination. So coordination is waiting for maybe 2 or more teams to do something so that you can carry on. Maybe that's waiting for like an ops team to provide you with a VM and a database. I don't know. But you're waiting for the 2 things to happen before you can proceed. Coordination. So in this case, the people writing code, they had to wait for both canonical data models to be updated, and then they were allowed to write some code. Just go around in circles. There's another type of wait time, which is scheduling. So waiting for maybe a scheduled meeting to happen. So think about architecture review boards or change request boards. You know, maybe your super senior chief architect folks and their people, you know, they meet once a month or so. So if you've got a big decision you need to have taken before you can proceed, you're going to have to wait a month maximum, on average 15 days, you know, before you can carry on. So that's the sort of scheduling problem. So architecture review boards. Fun fact from Accelerate, change request boards are predictors of low organizational performance. And I'm using that in the strict sense. So if you have a change request board, it predicts your organization will be in the low performing part of the sort of software development kind of world, industry, if you like. Just change request boards. So, and that's to do with having to wait for decisions to be made. The next thing is queues. So, you know, queues, waiting for stuff to go into the top of a queue and be processed until you can take something out the bottom of a queue. And here's some examples of queues. So, you know, someone requested some changes, but there's a bunch of changes that have been requested. So, you know, the next team will pick the top one. And if you've requested something at the bottom, you've got a long time to wait until it gets to the top. Waiting for architects to put together options for designs. You know, waiting for the integration team to pick stuff up. All these are examples of work sitting in queues, inventory sitting around, like basically losing you money, basically going off. Right? Anytime work is sitting in queues, you're actually losing money. So sometimes we actually have the worst of all worlds. We have all 3 at once. Now, this is an example of all 3. This is where you're waiting for an integration test environment to be scheduled. So you're waiting on other teams to finish their integration testing. Plus, you've got to schedule your work into a queue to go onto the integration test environment. Plus, you've got maybe a time slot that you have to hit. And if you don't hit it, then someone else will do. So all of these are different types of wait times, different types of ways in which work slows down whilst flowing through an organization. So a quick sidebar on generative science now. So generative science is this idea of using things like simulations to explore the natural world. Simple simulations to explore the natural world. Got a couple of examples. This is the first one. So this is flocking behavior in birds. So you can use agent-based models with really simple parameters to simulate the natural world. In this case, you've just got 3 very simple parameters, which are things like the turning circle, how far these agents can see in front of them and how fast they go. And in this case, nothing's happening, right? They don't actually flock. But when you have a slight tweak to this, slight tweak to the radius at which they can turn, over a very short period of time, you get this very complex behavior emerging of this sort of like flocking or swarming-like behavior that you see fish or birds do. And this is an example, as I say, of generative science using agent-based models. You can do other things with generative science, other things with agent-based models, other simulations. This is one that shows virus propagation through a population. Obviously, this is a very simple version. If anyone would like to know, this is NetLogo. Remember Logo? Turtles? No, people are shaking their heads. It's like a classic sort of learning tool for kids. I've used these Logo. Anyway, whatever. Come talk to me afterwards. But this is NetLogo, a more modern version, which you can use to build these agent-based models. And of course, you know, you can build much more complicated agent-based models. A lot of the work that was done to show COVID propagation through population during the pandemic was done using agent-based models. This is one using something called EpiRust that we co-published a paper with the university on. There's another one called Bharat Sims. We built this to look at the population in India and how COVID was spreading throughout the population in India, using these very simple models for agents who, how close do they get to one another? Are they wearing masks or not? Putting these very simple parameters in allows you to simulate quite, the real world. This is my favorite thing, the Gini coefficient. Using agent-based models, you can prove, more or less mathematically show, that trickle-down economics don't work, essentially. So you can, if you build an agent-based model based on the exchange of value, all the agents start with the equal amount of value and the exchange value between them. In every single run of the model, unless you put controls in place, one agent ends up with all the things, and all the other agents end up with nothing. That's basically economics. That's capitalism for you, unfettered capitalism. It is shown using these sort of models that trickle-down economics doesn't work. And they can actually produce the Gini coefficient by, so the Gini coefficient is the ratio of rich to poor, essentially, in the Western world, anyway, by implementing market controls. So they take the model, they put the market controls that the Netherlands has into the model, and out pops the Gini coefficient for the Netherlands. Anyway, maths. Maths says that capitalism is evil. I'm a bit of an old lefty, old hippie. Thought I'd get that one in there. Anyway, back to following the work. So you've got these different types of weighting, right? Different types of weighting. You've got synchronization, you've got coordination. So you've got synchronization, you've got scheduling, and you've got queuing. And interestingly, you can look at these types of wait times, and as Don Reinerson has done in his brilliant book, Principles of Product Development Flow. And you can extract a set of principles that allow you to reason about how work is flowing through our systems, how work flows through these different value streams. And you can use these principles to optimize these value streams. But you can also demonstrate these principles using agent-based models. So here's the first one, the principle of congestion collapse. When loading becomes too high, we will see a sudden and catastrophic drop in output. Now, we often hear about this idea of having slack in our teams, right? So not being used to our full capacity every time, having a little bit of space so that we can take on unplanned work and so on. Martin Fowler just wrote a Blicky entry on it very, very recently. And that's because of this thing, the principle of congestion and collapse. So as soon as you overload a system, you get this very, very quick sort of catastrophic collapse into chaos, essentially, when you've got too much stuff happening, when people are taking on too much work. And you can see this very simply using agent-based models. This is an example of congestion collapse on a motorway. So this is a number of cars going along a motorway. And you can kind of see that every now and again, they all back up, right? They all back up. But there's no accident going on here. There's no crash or anything like that. This is just behavior purely as a function of there being too much going on, too many cars in for one particular stretch of road. And we see this when we drive our own cars, right? You just get someone puts their red light on and then everyone else does, and suddenly everyone comes to a halt. And then starts again, comes to a halt, starts again. That is congestion collapse on the motorway. But the same thing happens on our teams. The symptom of congestion collapse is when essentially everyone's working really, really, really hard. You've got massively high utilization, but not much coming out at the end. And I imagine most of us have been in situations, that's the Welsh in me coming out, in situations where we've sort of experienced that, right? Where it seems as if it doesn't matter how hard we work, nothing seems to be produced. Right? That's because too much stuff is going on. We've got too much work in the system. And you can actually sort of tweak this, right, and use these principles to address congestion collapse. So the peak throughput principle, control occupancy to sustain high throughput in systems prone to congestion. So if we go back to the motorway example, we run that. Just by reducing the number of cars on the motorway, haven't done anything else, they're going the same speed, accelerating the same amount. Just by having fewer cars, you reach this steady state where you don't have a congestion collapse. We can do that on our own teams, right? We can implement things like working progress limits. We can limit the amount of work in progress so that we don't get overwhelmed and suddenly experience this sort of overwhelming congestion collapse effect. There's another one, actually. This is the second queue size control principle. Don't control cycle time, control queue size. So we talk a lot about cycle time. 4 key metrics talks about cycle time. It talks about, well, it actually talks about lead time to production, but they're really talking about cycle time, measuring cycle time, but actually measuring the queue depth, measuring how much stuff you've got sitting in front of your team will tell you the cycle time via Little's law, essentially, by a bit of maths. And also, it's a leading indicator. I'll try and explain why. So, with an example, hopefully you'll kind of resonate after being here or being at conferences. So how long at a conference do you have to wait for lunch? Or any other sort of event where you've got to go to a buffet and there's lots of people, right? Now, I know we had 2 tables here, I think, today. They opened at a particular time. So 1 p.m. lunch is served, say. It was 12:30 today, but 1 p.m. lunch is served. And what you've got is a bunch of people who've been sitting around, haven't been to any talks, right? So they just sort of start turning up and helping themselves, right? And then suddenly, at 10 past, all the talks finish, and then everyone else turns up for lunch, right? So you get this steady arrivals rate at the queue, going back to queuing theory, and then suddenly, boom, you get this massive load of people turning up, waiting for lunch. And what happens? Everyone's standing there waiting, right? Because you have to get in a queue, or for a beer tonight, it'll be the same thing. You'll be standing there waiting in a queue because everyone goes at once. Because the arrivals rate changes, but unfortunately, in these cases, the departure rate is normally constant. So the rate of departures, the rate of people, how quickly you can get lunch, is essentially constant. Now, if you were to ask someone after they had lunch, or ask someone this evening how long it took to get a beer, they go, I was standing in the queue for 5 minutes. But you have to wait until after they are served to ask them the question, right? So you have to wait 5 minutes before you know that people are waiting 5 minutes, if that makes sense. Self-referential. Whereas if you just look at the amount of people in the queue, that will tell you mathematically that it will take 5 minutes. So just by looking at the amount of people in the queue, just by controlling queue size, you can actually understand how long things are going to take in your team. So just by looking at the number of JIRA tickets or user stories you've got sitting in your backlog, that will tell you the average cycle time for a user story through your team. Right? Control queue size, don't control cycle time. Cycle time is a useful trailing indicator. And then finally on this bit, the batch size queuing principle. I did promise you something about batch size. Reducing batch sizes reduces cycle time. I sort of mentioned that, right, in that simple value stream map. If you deploy twice as often, you improve your throughput, right? And what you're doing when you deploy twice as often is halving your batch size. When you half your batch size, you double your throughput. Half it again, double it again. Half it again, double it again. It's the simplest way of improving throughput. In fact, it's kind of almost a consultant's trick that I'm letting you in on. Because basically, I can walk into any organization and say, well, how often do you deploy? And they say, oh, once a month, once every 3 months. I say, I can double your throughput. And they say, how? Well, we'll just deploy twice as often. I mean, it's like as simple as that, right? I know that sounds ridiculous. But what it means is, if you're deployed after 6 weeks rather than after 12 weeks, the stuff that's been deployed has been earning money for that 6 weeks, rather than sitting there in a backlog not earning money. This is just a graph showing the difference between 2 big batches going into production versus lots of small batches going into production. The stuff in the small batches starts earning money at this point. And by the time it would have gotten into production, it's already earned a ton of cash, or saved lives, or whatever it is that you do. In fact, Don Robertson goes on to say, batch size reduction can enable us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization. Awesome. We don't have to work harder. We don't have to add more people. Just deploy twice as often, and you double your throughput. I won't go into all of these principles from Don, because he's awesome, and you should read this book. It took me a while to grok it. There's something like 200 plus principles in it. So you kind of need to have maybe a bit of grey hair to kind of appreciate maybe all of them. But this is what he says about queues in particular. Queues create longer cycle time, increased risk, more variability, more overhead, lower quality, and it reduces your team's motivation. If I have to wait 3 months to see the code I've been writing in production, that's intrinsically less motivating than seeing it the next day. So, these complicated value streams, though, they aren't the whole picture. Back to complex adaptive systems. So they sort of started off, or I sort of heard of them via the Santa Fe Institute. So I started following the Santa Fe Institute based in New Mexico. This is kind of just post-chaos theory. Essentially, they started looking at this idea of complexity science, complex adaptive systems. And complex adaptive systems are made up of 4 different components. They are self-similar, so my cells are self-similar to everyone's cells in the room. They're self-organized, so there wasn't a central orchestrator creating James when James was made, because I am a complex adaptive system. They're complex, by which the whole is greater than the sum of the parts. If you put James into a blender and blend me up, right, into James soup, or whatever it is you get, and then pour that soup into a James-shaped mold, you don't end up with James at the end of it, right? You end up with James-shaped soup in a James-shaped mold. You get this, the whole is greater than the sum of the parts, and then emergent behavior. There's been a ton of research recently that points to the fact that complexity science points to the fact that different types of structure in our organizations, in complex adaptive systems, leads to different effects mathematically. It's just maths. Don't blame me. As I said, it's just maths. And what that sort of research points to is 2 different types of network having 2 different types of effects. So hierarchical networks essentially lead to economies of scale, right? So anytime you've got a hierarchical network, you get economies of scale and things slow down fundamentally. But small world networks, so social networks, based around small numbers of people, right, who are closely sort of related, not related, but who have high bandwidth communication, they lead to returns to scale. Essentially, without going into all the research, I've talked about this online a lot, if you've got hierarchies, things slow down, and if you've got social networks, things speed up. That's basically what it comes down to. Right? So in big organizations, when you've got very deep informational hierarchies, things are slower than in smaller organizations that have less deep informational hierarchies. Or in same size organizations that are organized via social networks, right? By small teams that are autonomous, decoupled from one another. AWS works like this. Jeff Bezos designed it to work like this, essentially, as a series of independent teams that are working, building new products side by side, but not dependent on one another. The informational hierarchy isn't very deep. As you add hierarchy, things slow down. Information in those big value streams takes much, much longer to go from one end, the idea, into production, and the other end, where you're earning money, than it does if you've got that really short 3-stage value stream. It's the bleeding obvious now, but there is maths to show this. And in fact, in organizations, and this is why Team Topologies talk about value stream aligned teams, in organizations you have these incredible kind of fractal informational structures, right? And at each point, as I showed in some of those value stream maps, you have these queues that are essentially blocking information flow, or you're synchronizing on other things, blocking information flow. And this is why things slow down and things get so slow. And this is why things like Team Topologies, talking about value stream aligned teams, means that things go faster. Autonomous, self-contained, decoupled teams, things go faster. So, I did promise you to show you how work works. I'm going to come to a bit now, agent-based models, complexity science, all the stuff we've learned about team topologies and queuing theory and all these things. Can we put those together to actually model the real world, right? Can we use these complex adaptive systems, Gen AI, generative science, and queuing theory to actually look at organizational designs and understand how team structures can be changed or altered or put together to optimize for flow? And as I say, I think we can. Turns out maybe we can. I've been working on this problem for about 4.5 years. I have a prototype, which I'll show you in a minute. It's a very simple prototype. And then it turns out bloody Google got there first. Of course they did. So they published this paper. You might have seen this. It made a big splash when it was published. Generative agents, interactive simulacra of human behavior. So what they've done is they've created an agent-based model where the agents use large language models to talk to one another. Right, so the agents have access to a ChatGPT-like thing, and the agents then use the ChatGPT-like thing to converse. And they do things like learn, they fall in love, bizarrely. They'll self-organize their own birthday parties and pass that information on to the other agents, and the agents will then turn up because they think, oh, it's a birthday party, I'd better go to that. And this was done in conjunction, Google Research and Stanford. Now, they haven't applied this to companies yet, but I think it's only a matter of time before they do it. They've also open sourced the code. This is what the simulation looks like. It's like a 16-bit little computer game, like The Sims, essentially. This is one of the agents. They've got a current action, what they're going to do for the day, and they use the LLM to plan. They say, okay, I'm a software engineer. Say, what should my day look like? Oh, well, you should run your morning routine, the LLM will say. Then you should go to work. Then you should do some work. Then you should have some lunch. And the agent will use that plan in order to, it's mind-boggling stuff. Anyway, so Google got there. They're modeling the real world using Gen AI and generative science, so agent-based models. And I think we can actually go further and use Gen AI and agent-based models to model actually what we do, as I think I sort of said. Because fundamentally, when we look at these value streams, as I mentioned earlier, we are kind of machines. Most of what we do is kind of machine-like. We take a thing, we do something to it, we produce another thing. Whether that's in a factory, or whether that's in our organizations where we're doing knowledge work, right? We're taking something that's less valuable, a user story, writing some code and making it into something that's more valuable, which is compiled code running in production. But it's the same thing as lawyers do, as supply chains do when we're moving oranges from Seville to the UK, say. There's just these little value-adding stages where we're taking a thing, performing an activity, and creating another thing. And so you can model that. You can model that using agents. You can model that using a series of queues, essentially, between agents. And you can create teams of these agents. This is the enterprise architect machine. Their job is to take requirements, documents, and create these solution designs. They take one thing in, do some work on it, produce another thing. That's one stage in this little value stream. You can model the different types of wait time between these agents and between teams. So you can model people going for meetings and how long the other agents have to sit around waiting for those meetings to go on. You can actually graph this and show what the value lost looks like. And you can do all this using things like behavior trees. That was the first attempt I made. Actually, the first attempt was something else, just a normal finite state machine. But behavior trees are a sort of a well understood form of AI in game development. And you can use behavior trees to model our behaviors, and you get this kind of complex, emergent behavior from modeling all these agents together. Yeah, and that's what the C# code looks like. Godot, by the way, if you're into game development, Godot is an amazing game engine written in well, it's actually not written in .NET, but you can write C# natively in it. And then eventually you can sort of end up with simulations of how teams work. So this is like halfway through a run of my prototype where you've got a bunch of people, a bunch of agents, and they're doing stuff. You've got developers and testers. The developers are writing code and committing it. The testers are testing it, sometimes finding defects, adding them into the queues and so on. And you can they do stuff, and work moves around, and sometimes it's blocked, and sometimes it's not. And you can test different types of process, whether it's agile or lean versus waterfall and so on. And then you can graph what happens in terms of lead times and in terms of value created by your organization. And in this case, we're showing the difference between an agile team and a, quote, waterfall team, where in a waterfall team, every time work has been done, all stuff has to be done in the previous stage before the next stage happens. So everything has to be analyzed, and then you can start development. Everything has to be developed, then you can start testing. And you can kind of see the difference in value delivered between agile, quote, agile, and, quote, waterfall, and the difference in lead times. So this is an ongoing process. I think lots of people are going to start doing this, modeling this sort of stuff. And hopefully I'll have a proper working piece of software that I can actually show you at some point, sometime soon. So I love this quote from Charlie Stross. I've sort of butchered it a bit. He's a British science fiction author. We talk about artificial general intelligence, and when are we going to get AGI? Is Gen AI, or these LLMs, are they a step forward towards artificial general intelligence? And he has a different opinion. He thinks that artificial general intelligence is already here. We call them companies, and we get paid to execute their algorithms very, very slowly. Essentially, we're just little machines, little cogs doing stuff, picking things up, doing a thing, passing it on, do a thing. Yeah. So there's a bunch of principles I said: congestion collapse, peak throughput, second queue size control principle, don't control cycle time, control queue size, and the batch size queuing principle. I'll leave you with that that thing I said about batch size reduction can enable us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization. So, to summarize, this is all the stuff I think we do that seems to work. This is how it works, how work works, by stuff flowing through our organizations, information being transformed from one form into a slightly more valuable form, how it works. And then underneath that, I think it all flows from these ideas from complex adaptive systems, queuing theory, maths, and so on. I think that's me. Yeah. Thanks for coming. And